As I said, there's more moving parts in our model of the cosmos. There are more things that do not remain fixed on the celestial sphere and just rotate with it, but yet rise and set, so are off the Earth. And the next most conspicuous one after the sun is our moon. Like the sun, the moon moves along the celestial sphere. It's not fixed. For the same reason, the moon orbits the Earth. It orbits the Earth in the same sense that the Earth orbits the sun, and in the same sense that therefore the sun appears to orbit the Earth, moving towards the east along the celestial sphere. But the moon orbits the Earth much faster. The moon completes one orbit about the Earth in what is called a sidereal month, which is about 27 1/3 days. This means its right ascension increases by 52 minutes per day. Now, as the moon orbits the Earth, it also rotates about its axis. We'll discuss next week why this is, but this means that we are always seeing the same side of the moon as it rotates around us. There's the same side of the moon that faces us. This means that while there is no such thing as the dark side of the moon, there certainly is such a thing as the far side of the moon. There are parts of the moon that are never visible from Earth, and those were first seen or indirectly seen by human eyes when the Soviet Luna spacecraft first orbited the moon. So this is why when we look up at the moon, every time we see it, it has this familiar look. We're always seeing the same side of the moon. The moon moves to the east along the celestial sphere by about 52 minutes per day. As we know, the sun also moves to the east along the celestial sphere. The sun moves much more slowly. The sun moves by about 4 minutes per day. The difference, 52 minus 4, gives us 48 minutes per day. This is the difference between the sun's motion on the celestial sphere and the moon's motion along the celestial sphere. Put otherwise, it is the relative motion of the moon relative to the sun. The moon is 48 minutes farther east relative to the sun each day than it was the day before. Since our clocks are attuned to the sun, this tells us that the moon rises, on average, 48 minutes later each day than it did the day before, and sets 48 minutes later than it set the day before. The relative orientation of Earth, Sun, and Moon therefore repeats, but with a period longer than a sidereal month, because that changes not by 52 minutes per day, but only by 48 minutes per day. Make the calculation. You see that moving at a rate of 48 minutes per day, the moon completes a full 24-hour rotation about the celestial sphere relative to the sun once every 29.5 days. That is what is called a synodic month. What repeats once every synodic month, therefore, is the relative position of sun and moon on the celestial sphere. This controls, of course, the time of day at which the moon rises and sets. For example, if the sun and the moon are 12 hours apart in right ascension, this means the moon rises about 12 hours after the sun rises, about at sunset, and sets 12 hours after the sun sets, about at sunrise, so the moon is up at night during that time of the month. And this repeats once every synodic month. In addition to controlling the times that the moon rises and sets, as we know, this relative position of sun and moon on the celestial sphere also controls the appearance of the moon, or what we call the phases of the moon, and the way that these two are related is best captured by the following beautiful demonstration. The best way to understand how the moon's position relative to the sun gives us the phases of the moon is to just do it. And to just do it, you need a source of light. You can use a light bulb, or if you prefer, you can just use the sun. Just go outside if you can't find a light bulb. Anything round. I have a white styrofoam ball here to play the role of the moon, and your head to play the role of Earth. The view from your eyes will give you the view as seen by people on that side of Earth facing the moon of what the moon looks like, and then you simply turn around to perform a complete lunation, to give you a sense of what this looks like in case you're not going to do it yourself, though I strongly recommend it. What we have here is on the left side of the screen, you'll see a setup in the studio of me holding a moon and turning around in the relative configuration, whereas on the right side, you'll see the image of a GoPro camera that's mounted to the moon, so it shows you the image of the moon as I see it. When the demonstration begins, the moon is in between the sun and the earth. It's on the line between sun and earth. And so the illuminated side of the moon, as we can see in this beautiful picture, faces the sun and therefore faces away from the earth. I see the dark side of the moon, and the moon will be nearly invisible. As I turn to my left, to the east, slowly the western side of the moon will become illuminated, and we'll see a growing crescent until after I've turned 90 degrees, we'll see a waxing quarter moon. Since the moon is now 6 hours or 90 degrees to the east of the sun, it will rise 6 hours after the sun. In other words, the waxing quarter moon rises about at noon and sets about at midnight. As I continue to turn to the east, the illuminated part of the moon will grow and become gibbous until at last, when I'm 12 hours away from the sun, I will see a full round moon illuminated. We're going to have to switch cameras at some point to give you the full view because of studio limitations. Don't get confused by that. 12 hours to the east of the sun, the full moon rises at sunset and sets at sunrise, and so the full moon is the only moon that is really up all night and only during the night. You'll note that to give us a view of the full moon, I had to tilt the moon's orbit. I'm holding it way above my head. We'll get back to that in a second. As I continue to turn to the east, now the western part of the moon is losing the sunlight. I see the eastern part of the moon illuminated. It is a waning gibbous moon, and when I reach 90 degrees to the sun again, I have a waning quarter moon. The waning quarter moon, which is 6 hours to the west of the sun, will therefore rise 6 hours before the sun. In other words, rise about at midnight, set about noon. This is the moon we see in the morning. Finally, as I continue turning to the east, the moon becomes closer to the sun in the sky. Only the eastern edge of the moon is illuminated. I find a waning crescent moon, and after a full synodic orbit is passed, the moon is back in line with the sun, and again I see only the dark side of the moon, and we're back to new moon. So, what I hope you saw, and I do encourage you to do it yourself, it's really fun, and you can show it to your friends and family, is that over the course of a synodic month, as the moon orbits the earth relative to the sun, the shape of the visible part of the moon changes in the sky, as well as, because of the relative position of moon and sun, the rise time. So the new moon, when the sun and the moon are roughly at the same right ascension and the moon is completely dark in the sky, rises at sunrise and sets at sunset. The waxing quarter moon, when the moon is about 6 hours of right ascension to the east of the sun, rises 6 hours after the sun. So the waxing quarter moon rises at noon and sets around midnight and is visible all afternoon. The full moon, where the moon is 12 hours of right ascension ahead of the sun, in other words, on opposite side of the sky, the full moon is the only time that the moon rises at sunset and sets at sunrise. And the waning quarter moon, where the moon is 6 hours to the west of the sun, or 18 hours to the east, the moon being 6 hours to the west of the sun, rises 6 hours before the sun, in other words, rises about at midnight and sets about at noon, and the waning moon is visible all morning. So when you see the moon in the daytime, you should not be surprised, but should you ever see a full moon at noon, something has gone terribly wrong. So both the phases and the periodic change in moon rise and set times are completely understood in terms of this model where the moon reflects sunlight and what we see depends on the angle between the moon, the sun, and the earth. You can simulate this. You can go to the simulation page of the University of Nebraska-Lincoln and get a less three-dimensional version. But I encourage you to construct, take a light bulb and a ball of some sort and make yourself a moon.